Okay. So, we are considering optimal filter, right. We had this these are the filter coefficients. There is a 0 bin WSS process, real WSS, YN, and it should be a good estimate of a targeted sequence called desired response, so that error, its variance is minimized. Okay, epsilon square, which was is real. So, mod E square or E square they are same, because E square n expected value, that is the average power. Because of WSS nature, this thing epsilon square is independent of n. Okay. And then you have shown that this is, in fact, we worked out the formula for epsilon square, and we had W vector was this W0, W1 dot W n minus 1. All the filter coefficients stacked, input data vector, all these were defined in the last class. So, Y n is W transpose X n, this we have seen yesterday in the last class, and we also worked out this expression, that is sigma d square, which is the variance of d n minus twice W transpose P, which is a linear first order terms in terms of W 0, W 1, all that. This is not second order, but there was a second order term W transpose, this row vector or matrix W, or matrix into W. So, all components of W will be present in the resulting vector elements, or W is a column vector. In every element of the column vector, all the components of W will contribute, and then they will again get multiplied by another term, another W term from this. So, essentially it will be a second order thing, either W 0 square, W 1 square, W 2 square kind of terms, or W 0, W 1, W 1, W 2, W 0, W 2, like that. Okay, together this is a second order thing, and if we can then minimize, if we take partial derivative equal to 0 with respect to each of the weights. Okay, then we get n equations, because n derivatives, and second order stuff when derived, it will give rise to first order equation. So, we get first order equations total n, capital N in number, we solve them and find out the optimal one. This is what we are doing, and R was, though defined yesterday, it is the input autocorrelation matrix. It follows the Toeplitz structure, periodic symmetric Toeplitz structure, and P was the cross correlation vector E of this x n above, this x n will be here, all the components of x n, the x n vector times the scalar d n. Since x n and d n they are jointly stationary, that is why this vector also independent of n, like capital R is independent of n, because x n is jointly stationary, x n is stationary, W s s. Okay. So, then I defined this total derivative operator, okay, which is what, that if you have a function f, it is nothing but you are taking the partial derivatives and stacking them in a column, del f with respect to del W 0 dot dot del f with respect to this. Okay. So, then each of the partial derivative of epsilon square with respect to W 0, W n minus 1, W n minus 1 will be 0. That means, if I have instead of f this equal to 0. So, basically it will mean capital N number of partial derivatives is equal to 0. So, I will get, and second order stuff derived will give rise to first order stuff, will give rise to first order stuff. So, I will have capital N number of first order equations, linear equations, I solve them. That is my game plan. Now, to do this, first see if this sigma d square is differentiated with respect to any of the weights, I get 0 because sigma d square is independent of weights. So, this term I do not have to bother about. W transpose P, W transpose P is what? W0, P0, W1, P1 like that. Okay. This P is like, you can name them P0, 1 element, P1 dot 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 Pn minus 1. So, W transpose P we know it is W0, P0 dot 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 dot, general term may be Wk, Pk, and lastly Wn minus 1, Pn minus 1. So, if I take the partial derivative of this with respect to any of the weights, say del Wk of this W transpose P. So, right hand side if I find that only here I got Wk present, no other term has Wk. So, other terms will disappear, Wk Pk when differentiated with respect to Wk will give rise to Pk. So, if I now stack the derivatives like del W0, that will be P0, del W1, that will be P1 because P0 P1. That means, if I stack, that is del W, this term W transpose P, it will be all this P0, P1, P2 like this, which is P vector itself. Okay. So, one term will be minus 2 P. So, one term is minus 2 P, minus 2 W transpose P differentiated gives rise to P. So, minus 2 P, and then another term will come from here, but that requires more involved derivation which I will do now. W transpose R W, we have got this is nothing but W transpose R W, I take it together. So, it is a matrix into a column vector. So, it is a column vector. Okay. You can call it V. So, this is nothing but W0 V0, W1 V1, W2 V2 and their summation. So, it is Wi Vi. Okay. V is all the terms are indexed like this. V is a column vector R W, and this product W transpose V, row vector, column vector. If you do this multiplication, you will have W0 V0, W1 V1 and dot dot dot. This is what you have. But Vi, now consider V alone. Vi means what? This is your R matrix and this is your W vector. W vector means W0, W1 dot 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 Wn minus 1. So, R into W will be a V vector. Ith component of that vector means, if I is here, that means you have to take this row, ith row times this, that will be the ith component Vi. This ith row will be Ri0, Ri1, Ri2 dot 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 Rin minus 1. Okay. So, Ri0 W0 plus Ri1 W1 plus Ri2 W2 like that. So, this product Ri, you bring another term J and Wj, Ri and J will be from 0 to n minus 1. So, Ri0 W0, Ri1 W1, Ri2 W2 like that added, and this Wi will be here. This is what it is. So, suppose I want to apply just this partial derivative del Wk for some k, a general weight I have taken Wk, k could be 0, 1 up to n minus 1 on this. This is what I have to apply on this. So, once Wk has been fixed by you, my next step is, first in this summation I goes from 0 to n minus 1. So, 0, 1, 2 dot 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 n minus 1. So, it will become I equal to k also once. That case I separate out. separate out on this side Wk, Wk, that is I equal to k and R I equal to k. So, R k j W j. You understand? I equal to k case. So, W k with I is k and then again put k here, I is k and so k j W j, the same summation. That is I equal to k case I separately write. And then here I write I equal to 0 to n minus 1, but I also write I not equal to k. So, it goes from 0 to n minus 1, but it skips kth case and W I inside there is no change, whatever I you choose that I comes here. Now, if I differentiate this with respect to W k, you remember outside I have W 0, W 1 up to W n minus 1, but never I have W k. So, this is like a constant because it is not W k. Inside this summation for every W I, inside the summation I have R I 0 W 0, R I 1 W 1 dot 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 R I k W k. So, there is one W k inside R I k W k and other terms. So, if I differentiate these with respect to W k, I will get R I k, others go, they disappear because they are not, I mean no W k present there. So, R I k W k, when I differentiate that particular term in this summation with respect to W k, I get R I k. So, this summation gives rise to after derivative, that is if you do this, it gives rise to summation R I k, I equal to 0 to n minus 1, but I not equal to k. And now, here I have got W k here also, and inside the summation j goes from 0 to n minus 1. So, j will become k once, so that time I have W k or k k. So, W k and this. So, it is a product of two, this one and this one. So, you know the differentiation rule, I will first differentiate with respect to this without changing this and then differentiate this without changing this. Okay. So, if I differentiate this with respect to W k, I get this term. And now, if I hold this fixed W k, if I differentiate this with respect to W k, I get R k k W k differentiated, W k goes R k k. So, R k k and W k fixed here. So, R k k W k. Now, you see I equal to k is not present here. Suppose I equal to k was to be present, then that would have been a term W k R k k, and that is what it is, W k R k k. So, I can as well absorb this in this summation and remove this I not equal to k. Okay. So, it will be R I k W I and I from 0 to n minus 1. No longer I not equal to k, that is absorbed in the summation. And another term R k j W j and j equal to 0 to n minus 1. Okay. Then R is symmetric matrix, Hermitian, real Hermitian, so symmetric. So, R I k is same as R k I. So, R k I W I and R k j W j, both j and k, j and I are from 0 to n minus 1. So, the two sums will be same. Whether you put j here, you can change the index from j to I. You will still have the same number of terms, same terms, R k 0 W 0, R k 1 W, like that. So, if you change the index from j to I here in this summation, it does not alter anything. You are covering the same range. So, R k 0 W 0 when I equal to 0, R k 1 W 1 and like that. So, no change whether you are using j as the index or I to replace it. So, I replace j by I here and r I k is same as r k I. So, I will have r k I w I again r k I w I, same summation. So, it will give rise to twice r k I, or maybe instead of replacing I j by I replace I by j. Okay, I am just more fond of that, replace I by j. So, it will be r k j w j, r I k is r k I and then replace I by j here. So, r k j w j, same summation. So, j equal to 0 to n minus 1. Okay. Now, look at this summation r k 0 w 0, r k 1 w 1, like that. What does it mean? That if I have the R matrix and kth row and then W vector, so I have got kth row. So, R k 0 W 0, I have got R k 0 W 0, R k 1 W 1, R k 1 W 1, and so on and so forth. So, basically it is nothing but kth row times this vector, that will be the derivative of this W transpose R W with respect to W k. So, if I want to differentiate W transpose R W with respect to W k, I have to target the kth row and then this product. So, when it is W 0, I have to target the top row. When it is W 1, I have to target the second row. So, top row times this, that will give me derivative of this with respect to W 0. Next row times this, that will give me derivative of this with respect to W 1 and dot dot dot. So, if I want to put all the derivatives and stack them, it will be just this resulting vector R times W. This row times this will be, if you carry out the product R W, this will be the top element. But what is the top element? This times this will be the derivative of W transpose R W with respect to W 0. So, del of this del W 0 will come in the first guy. The next row times this, that is same as from this theory, derivative of this with respect to W 1. So, this matrix into vector, if I carry out the product, next guy from top will be derivative of this with respect to W 1 and dot dot dot. So, derivatives are stacked. That means, if I now take all the derivatives and put them in the stack of this quantity W transpose R W, it will be nothing but there is a 2 and R and W. All right. So, 2 R W. So, going to the previous page, the other term is 2 R W. And for minima, every derivative should be 0. So, this should be equal to a 0 vector. This is a stack of the derivatives, partial derivatives. Each partial derivative of epsilon square with respect to W 0, W 1 and this should be 0. So, all the derivatives are stacked here. This is the expression of the derivative. So, that should be equal to 0 vector. So, now then that means 2 cancels, you can take minus p to the right hand side, R W is p, which means W, which is the optimal weight now, is R inverse p. R is invertible because we are assuming R to be positive definite, not just Hermitian or symmetric, it is positive definite, which is a very standard assumption, and this we discussed at length earlier. So, this is that optimal filter expression R inverse p. Okay. So, W opt, I write separately, is R inverse p. Okay. Then only this error power, error variance, expected power is minimized. If I choose these coefficients of this vector W opt here, W 0, W 1 and W n minus 1, if I choose from this vector. All right. one thing you see, if I know that error E is dn, sorry, En is dn minus W transpose Xn. All right. At W, if you choose W opt, then this is minimized. E square n minimized. Okay, W opt. Now, if I am to find out correlation between every component of x n vector, that is x of n minus 1, x of n minus 2 dot 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 with E n, okay, then what is the result? So, I take expected value of x n vector into E n. So, if you write the x n vector fully here, then first term will be x of n into E n. So, correlation between x of n into E n, expected value, then x n minus 1 E n, another correlation between x n minus 1 to E n, then x n minus 2 into E n, correlation between x n minus 2 to E n, and like that. Suppose I want to calculate this. Then E n is a scalar. So, scalar is like a 1 by 1 matrix. I can write it also as E transpose n, because for a scalar which I can view as 1 by 1 matrix, its transposition is itself only one row, one column. So, E n is same as E transpose n. If I substitute that E transpose n here, that is E transpose n, that is transpose. So, x n d n, d n transpose is same as d n. So, E of x n d n transpose, that is x of d n, x n d n, that is my p vector, minus E of x n, and transpose of this will be like A matrix, B matrix, A B transpose is B transpose, A transpose. So, it will be x n and then x n transpose W transpose transpose, that is W. Another day I told you, since this is the random part and this is constant, you will get the same thing if you take W out and apply the E on this matrix. X n into X transpose is the matrix, column vector, row vector. So, if you apply E on every element of the matrix and then carry out the product, you will get the same thing. If you do not do that, if you do this x n into X transpose in this matrix, multiply this vector by the matrix, then apply E. E will not work on the elements of this, E will still work on the elements of this product matrix, okay, x n into X transpose, so you will get the same thing. So, I can put it here, and this is my R, and this W is W opt, that is when I use W opt, which is R inverse P. So, R inverse P, R and R inverse cancels, identity matrix. Identity matrix times P is P and P minus P is 0, which means every element x n minus 1 dot 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 are uncorrelated with E n. This is an important result. All right. Now, we have seen that optimal filter depends on two things, R and P, R matrix and P vector. R matrix is the input autocorrelation matrix. Now, that may not be fixed always, because input statistics can change, okay, depending on circumstance. Like say one person is speaking, his voice has some kind of autocorrelation and the person changes, or if in the word spoken by the person changes from time to time, Okay. So, autocohesion matrix changes, P vector changes, like that. So, if they keep changing, then I have a problem, because if they do not change, I know R matrix, I know P vector, R inverse P I calculate offline. So, I get the FIR filter coefficients W of vector in that vector. So, construct an FIR filter forever, construct the hardware forever using those coefficients and carry on filtering, I will be very happy. But if R matrix and P vector keeps changing from time to time, then right now maybe I have an optimal filter for the correct R, correct P, but after some time this will not be the optimal filter, because R has changed, P has changed. Point is, can I, like a mad guy, every 10 seconds or every 10 minutes or whatever, from time to time recalculate W opt, then break up, destroy, break up my hardware and reassemble my hardware, again run it for some time? I cannot do that, nobody can do that. Rather, better will be if the filter has an learning mechanism or training mechanism by which it can learn about the changing statistics of input and cross correlation and autocorrelation things from the data itself, and it adjusts the filter coefficients clock to clock to clock, nth clock to n plus 1th clock to n plus 2th clock, so that finally filter weights again converge to new value of R inverse P, because R has changed, P has changed. So, W opt has changed. So, that adaptation mechanism will make sure that the coefficients now again change, go on adapting clock after clock, but finally they go to again this optimal one, which is a new optimal, because R is now new, P is new, and it will continue. Such a filter is the filter of our interest, and that is called adaptive filter. Now, to go to adaptive filter, there is an intermediate step where we still obtain this optimal filter only, but not by this method of R inverse P, by an iterative method called steepest descent. We will move to this first. This is an intermediate step to get at the adaptive filter belonging to least mean square LMS family. So, we will cover that in the next class. Thank you very much.